The purpose of this video is to go back to section 12.6 and justify the formula that we used for the storage cost of a particular good produced over the course of a year. In section 12.6, the example that we were working on was for CDs, but it could stand for anything in general. We'll start here by naming some variables. So we're going to let D stand for the demand for our good, whatever it is that we're producing over the course of a year. X is going to be the number of units that we produce in each production run. T is going to be the amount of time that's gone by, and our time in this case is always going to be measured in years. Finally, C is going to be the total storage cost per unit produced per year that's gone by. A quick note before we go on here is that T doesn't have to be measured in integer years. So for instance, we could have T equal 1/12 if we wanted to measure 1 month going by, or T equals 1 over 365 to measure 1 day going by, and so on down the line. The first thing that I want to look at is the number of units that we have stored as a function of time, and in this case what we're looking at here is just for the first production run. You'll repeat this for the other production runs, and we'll take care of that later, but what we're going to talk about here is just for the first production run. First of all, you'll notice that the y-intercept, so to speak, in this particular case, occurs up here on this vertical axis at x. And the reason for that is because x is the number of things that we're producing at time t equals 0. We just assume that we instantly produce x units. The slope of this line is the rate at which our storage, our number of units being stored is going down. We're selling these units at a rate of D. So D things per year, you can think of that as D divided by 365 things per day and so on down the line. So the rate at which we're selling these things is D. And because we're measuring the number of things that we're storing, the slope has got to be negative. So the slope of this line is negative D. The upshot of that is once we know the slope, it's easy to write down the slope-intercept form of the equation of this line, which in this case is x minus dt. And this is going to be the number of things that we have stored in our warehouse after t amount of time has gone by. That is to say, after t years have elapsed. The next thing that I want to take a look at is to find the t-intercept of this graph. And what I mean by that is where this graph intersects the t-axis down here. As usual, we do that by taking the equation of the line and setting it equal to 0. We use that to solve for t, and what we end up with is t equals x divided by d. I'll mark that on the graph as the t-intercept, so that's at x divided by d. Next up, I want to take a look at a very particular point in time. Let's just call that point in time t, right? So just to be sort of general here. And what I want to say is that the number of things that are being stored at that particular instant of time is x minus dt things that are being stored at just that instant of time. Now, of course, we're selling these things at a constant rate. So as soon as we go just a little bit this way from that value of t that we're interested in, we've now sold some things and we're storing fewer things. But let's just assume for a second that what we do at that point in time t is store exactly x minus dt things. In other words, the top of this rectangle, we're just going to assume that just for an instant we stop selling anything and the top of this rectangle is flat. This will get taken care of in just a minute. But what we want to look at is, we're just going to assume that the number of things that we're storing is constant for just a very small amount of time. And we're going to call that small amount of time delta t. In just a minute, we're going to take the limit as delta t goes to 0. So it's going to sort of work itself out in the wash. And this rectangle is going to get sort of very, very close to approximating this line at that t value t, we're calling it here. So what I want to do is find the total amount of money that it costs to store the x minus dt units over this amount of time, delta t, after t years has gone by. And the way to do that is as follows. The total cost for storing these x minus dt units is the number of things that we're storing, multiplied by the price that it costs to store each one of these things for a year, multiplied by the time that we take to store these things. So the number of things that we're storing at this particular point in time is x minus dt, The price is a constant. That's the amount that it costs us each year, and we've called that C. The amount of time that's elapsed here that we're storing these x minus dt things is what we're calling delta t. Next up, we're going to do this for a bunch of different points in time. And we're going to calculate that storage cost for each of these points in time, and we're going to sum all of those storage costs up. Now, this picture over here should start to look familiar at this point. It looks a lot like what we did when we defined definite integrals in section 13.4. So we're going to sum all of these things together, and then we're going to take the limit as delta t goes to 0. And what that's going to buy us is the fact that these rectangles are going to get smaller and smaller and better approximate the cost that it takes to store these things over the course of an entire year. So once we take that limit as t goes to 0, what we're going to get is a Riemann sum, and in that limit as t goes to 0, what we're going to get is the definite integral, which is recorded here. You'll notice that the bottom limit is at t equals 0. That's when we start our production run. And our production run is completely sold out at time t equals x divided by d. That's the t-intercept that we saw in the last slide. What this is saying is we now have no more things to store at that point, and we have to start our next production run. So what this entire definite integral tells us is the total amount of storage cost that it's going to take us just for the first production run. Now from here, this is a straightforward arithmetic or an algebraic problem to work out because we have the fundamental theorem of calculus. So we apply the fundamental theorem of calculus, we take the antiderivative here, and we evaluate it at the lower limit and the upper limit. So keep in mind here that this lower limit, our variable of integration is t, so our lower limit of integration is from t equals 0, not x equals 0. And then finally, our upper limit of integration is at t equals x divided by d in this case. We plug those things in as we usually do. That takes us down to this point. We do a little bit of simplification, and what you're going to get is this quantity here. Now, I'm going to write that quantity in a bit of a funny form over here, and you'll see why that is in just a minute. So what we just found was the total cost to store our units in the first production run. Every production run is going to be like this, so we can look at this as the total cost per production run, not just for the first production run. Now, next thing that we need is the total number of runs that we're going to be making over the course of a year. And what we know is that we have to sell D units, that's our demand, over the course of the entire year. And each production run we produce X things. The number of production runs multiplied by the number of things that we produce in each run is going to give us the total number of things that we sell over the course of a year. So we solve this equation for the number of production runs, and what we end up with is that the number of production runs is our demand divided by the number of things that we produce in each run. And that's what you're seeing right here. So our total storage cost for all production runs over the course of a year is the total cost per production run, and that quantity is coming from this quantity up here. We're just copying it down, multiplied by the number of production runs that we make over the course of a year. And again, that's just this quantity here being re-recorded down here. We multiply those two things together, and you'll see now why I wrote things in this funny way above, because these two guys are going to cancel each other out and just give a multiple of 1. What that leaves is this quantity here. Remember, C is the amount that it costs us to store 1 unit over the course of a year. X is the number of production runs, and this factor of 2 that shows up in the bottom comes way back from up here in the antiderivative. So these two things are intimately connected in this particular case. So back in section 12.6, when we were talking about that sort of mysterious factor of 1/2 that showed up, this is where it comes from.